Good morning. Today I'm going to present you my Physics 2211 Lab 2 of motion of a falling object. The purpose of this lab is to exemplify the physics principles of Newton's second law with gravity and show that in real life there are more forces involved in a falling object. Newton's second law is total force equals ma and force of gravity equals mg. The principles in action here is Newton's second law, which describes how the force exerted by Earth on an object causes an acceleration of around 9.8 meters per second squared. This is determined by the gravitation formula, and the gravitation principle shows how the force exerted by the Earth on the object can be calculated to be 9.8 meters per second squared with this formula. So the experiment. The object selected to analyze was a ball. The center of the ball was tracked with tracker for each frame. The data position versus time were recorded by the app. The origin was set to the starting position of the ball. The movement down is in the negative y direction. Here's the video. So the system and the surroundings. The system is the ball, and the surroundings are earth and air. This is the force by gravity, and this is force by drag by air. So now the description of the computational model. The total distance traveled was 155 centimeters for the model with drag, with b, the constant of drag, being 0.15. The total distance was 167 centimeters for the model with no drag. The model printed the data for each time step with its corresponding position. Here's the velocity with drag, which is slightly curved, and this is the velocity with no drag. So the comparison. All curves follow the projectile motion. All have an increasing velocity downwards, and the model with drag and the experimental end at the same place. The differences are that the model with no drag travels more distance. The experimental position, y position, doesn't look smooth, and the experimental positions look a little above the model with drag, as you can see here. Possible sources of error. The drag constant b may be different in real life, as I don't know how to calculate it. It was set by trial and error, fixing its value when the final position was very close to the actual final position. The non-smoothness of the experimental y position may have been because the tracker didn't really track the center of the ball at all times. So, what does this mean? Which models, if any, predict a terminal velocity? The model with drag included could predict a terminal velocity for a prolonged time. The force of the drag is proportional to the square of velocity, which is increasing at this time. Since force of gravity is constant, there must be a time where the force of drag equals force of gravity, having a net force of 0 and therefore having a constant terminal velocity. So, what if the object was initially thrown downward? Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? The terminal velocity would still be the same because it depends only on velocity, not on initial velocity. As evident from the graph, the velocity would still flatten out at the same velocity, but it would happen faster. So this is the link for my simulation and computational model. Thank you.